So, continuing our discussion on the temperature control, in electrothermal atomic absorption, it is possible to heat the tube and hence the sample, because we put the sample inside the tube. So, we can heat it at a controlled rate in a series of stepwise increments. This is the beauty of electronics. This permits the removal of unnecessary matrix components in the predetermined manner. So, it is possible, suppose you heat it to 100 degree centigrade or 90 degree centigrade within 1 second, that means heating time is 1 second, temperature is reached at 90 degree centigrade, and then you can hold it up to for about 1 minute, 1 second, 2 seconds, 3 seconds like that, because you are handling microliter quantities of the sample here. Okay. So, I can heat it to 90 degrees within 1 second and then raise it to 120 degrees at 2 degrees centigrade per second. That means, from 90 to 120 degrees I can heat it at 15 seconds. Okay. So, within that time I can the sample gets evaporated, all the moisture will go, and I can hold it for 10 seconds to remove the remaining water. This is only one example of how I can control the heating for different chemical removal. One is water, another is organic substances, organic solvents, etc. Similarly, other temperature programs may be incorporated to remove organic matter. I can heat it to about 400 degree centigrade. Suppose I am analyzing an organic compound like milk powder. So, milk powder mostly it will be organic material only, lactose, carbohydrates, proteins, etc. So, I can put that, dissolve it and put that sample in the graphite tube, heat it to 90 degrees, and then all the water will go. Whatever remains is organic matter around 120 degrees, 90 to 120 degrees, then I heat it to 400 degrees. Then what happens? Most of the carbon material, protein and other tissue materials, etc., they will burn off. They form vapor or burn off, and then that will be swept away, because I keep the argon flow constant. That means, while heating I am keeping the argon flow. So, whatever comes out of the system inside the tube should be swept away. So, I can heat it to 800 degrees afterwards, maybe 900 degrees. Then what happens? All other inorganic salts also, like chlorides, sulfates, etc., they decompose, and then chlorine will go away around 800 degrees. Sodium chloride itself will melt around 800 degrees. So, any sample containing sodium and chloride will go. So, if you want to analyze urine, a lot of sodium chloride will be there, right. 1% sodium chloride will be there in almost everybody's urine. And then you can, if I want to analyze some elements in seawater, there 3.5% of chloride is there, sodium chloride is there. So, I hold it to 800 degree centigrade, most of the sodium chloride will go away. So, around 1000 degrees, most of the sulfate will go away. So, the organic matter, inorganic matter, and the salts and etc., and all other concomitants are removed by temperature programming, and only suppose I heat it to around 1000 degrees, everything is gone. What remains? What remains is only metallic elements, maybe their oxides, okay. And the oxides get reduced to metal because of the carbon atmosphere. So, for the atomization, a maximum heating rate we require, because after 1000 degrees nothing is left, nothing organic is left. At that time I increase the heating rate to very fast to 3000 degrees centigrade, okay, 2000 degrees. So, for the atomization maximum heating rate is required, that means ramping. So, within here I had mentioned that 2 degree heating rate per second. Here I heat from 1000 to 2500 in in 1 second or 0 second, that means maximum heating. So, then what happens? All the material that is present will be atomized, okay. And the pre-treatments, such pre-treatment procedures can be standardized for each and every matrix, for food, for blood, for metals, for environment samples. For all these things, these pre-treatment methods can be standardized depending upon what they want to work with. And then in the preliminary experiments, before we can do the standardization before optimizing the temperature program. So, what is a temperature program in graphite furnace is to remove the concomitants. Concomitants means other matrix elements that are present along with the sample without our intervention. That means a plant extract will have salts, organic substances, etc. All those things are called as concomitants. Okay. So, this already temperature programming has given rise to a sort of analytical concept that is known as stabilized temperature platform concept. So, what we are doing is, because it has the detection limits of Labo furnace are 2 to 3 orders of magnitude higher than the Massman design, because the sample after vaporization is not in equilibrium with the volume time of the volume or time or temperature. So, the Sturgeon and Chakravarti found that 60% of the atoms formed diffused to the cooler ends of the graphite tube, which was around 1500 degrees compared to the middle temperature of about 2000 degrees. If you go to Massman design, you will see that the two ends of the yes, this is the Massman design. If it is 2500 degrees in the range B here, it will be 1500 near the edges. So, this is what Chakravarti found out. And this was not tenable, because we want uniform temperature throughout the tube. So, equilibrium with time is more difficult to achieve, but even then, so this has given rise to the graphite tube and platform arrangement. What they did, another improvement in the graphite furnace is, they put a platform inside the tube. You round tube, you put insert a small graphite plate inside that, make a groove and then insert it, so that the plate is inserted, it does not touch the bottom, it does not touch the sides, it will touch only the sides, but it can be, it will be almost hanging in between. That means, I make a small groove here and then insert it this platform, and this is the hole through which the sample is put. So, I take a micro pipette, put the sample here on this platform instead of the graphite tube. If I do not put the graphite platform, I will be putting it on the tube, and then the tube will be heated more here and less here at the edges. So, this problem is avoided because this platform is uniformly heated, because it is not in, it is in contact only with the sides of the graphite tube. Okay. So, this is how it looks, the inserted graphite tube, so that the sample can be put here on this graphite tube, and this temperature is more uniform. So, it is called as stabilized temperature platform concept, STPF. Okay. So, Labo proposed that the sample must be dispensed on a loosely fitted pyrolytic graphite platform. What he said is, do not take the graphite tube which is pyrolytic, but make the pyrolytic platform also. The platform is a small 3 by 5 mm graphite plate inserted into the tube. Okay. So, he said even that platform you have to make it pyrolytic. That means coat a carbon layer, impermeable carbon layer, that is pyrolytic platform. What he said is coat that also with the carbon, and that will be heated only by the radiation and not by the direct contact. So, radiation heated material will be heated uniformly instead of contact. So, such an arrangement does not permit heat conduction at right angles to the plane of graphitization. So, such an arrangement in temperature follows the tube temperature rather sluggishly, which permits better equilibrium conditions, because the tube gets heated fast, but platform gets heated slowly. So, when the tube is at maximum, this will slowly heat up to that temperature. So, there is a certain amount of delay in which the platform gets heated, and the platform is under equilibrium conditions. So, such a system has been proved that interferences are very low. So, this is a wonderful concept. And another concept that is in graphite furnace technology is automation. So, what is required is the in graphite tube, the sample must be invited through a micropipette. Every time you have to do analysis, your sample is in a bottle or a tube like this. Your sample is in a tube like this. You have to open it, put your micropipette, suck the sample, put it in the graphite tube, and the graphite tube, then you close the Massmann top cover and then do the temperature programming and heat it. So, there is certain amount of operator skill required, because the diameter of the tube in which the sample is put is about 1 mm. So, the micro tip should enter there to discharge the sample. So, what people did is there may be certain amount of difference in the sample delivery, even if it is of the order of 1 or 2% in the micropipettes. So, the sample to be handled is rather small, 5 to 100 microliter, but the sensitivity is rather high. The sample has to be introduced exactly in the same place. That is possible if you can put the sample on the platform. So, every time you have to insert it through the sample onto the graphite. There is also the risk of sample contamination with the graphite hole edges, and pipette tips can get contaminated. All these factors lead to poor precision with manual pipetting. That means, every time you do a manual this thing, you are open to some sort of interference or contamination. So, moreover, micropipette taking sample, putting it, and then again analyzing, doing this, that, etc., it is cumbersome. So, what people thought is, why not I design a CARUSEL in which the sample is picked up and then a robotic arm can pick it up, take it there, put it, insert it into the graphite tube, come back, and by the time it comes back, the CARUSEL will rotate, another sample will be ready for pickup. So, that kind of programming can be done, that is known as automatic pipetting. So, this automatic pipetting concept is very new, and nowadays of course, it is being employed for all kinds of samples, including spectrophotometry, gas chromatography, HPLC, etc., but it all started with graphite furnace technology. So, this was around 1970s, and several programmable automatic dispensing units are available now, and the tubes need to be made of Teflon, and then they are available in the market, and also they are offered as standard accessory in graphite furnaces. So, the reproducibility with automatic dispenser is about 1% with an RSD of 0.4% compared with 5% is the reproducibility in manual pipetting. That means 5% error is there for micro pipette which are handled by persons, but RSD is about 3.2%. What is RSD? Relative standard deviation of the delivery of the sample. Okay. So, that is micro pipetting quantity. So, this is how the sample carousel looks. Here you can see this is the robotic arm. Here you can see this is, there is a Teflon tube here and the robotic arm is here. Graphite tube will be somewhere here inside on the optical path. So, this robotic arm will come here, then come here, pick up the sample, rotate and deliver the sample there, comes back, and here once it sits in its original place, there will be water flushing, and this flushed water helps to clean up the tube. And then again when it is ready, the robotic arm will lift and move on to some other position and pick up the sample and redo the analysis. That means whole auto operation of atomic absorption can be automated without any human interruption. If all I have to do is prepare all the samples to be put in these holes and then go for coffee or lunch or something and come back. By the time you come back, when everything is automated, it would be ready for the interpretation. So, the whole of atomic absorption process can be automated using this kind of samples. Okay. So, this is the difference between manual versus automated pipetting. So, you can see that I have plotted absorbance here, and this is the, I have taken some sample and plotted the absorbance through the automatic pipetting, that is through the CARUSEL, and here I have done it manually. So, you can see that 99% most of the time my readings here are between 0.34 and 0.35, that is absorbance seconds, but all of them are between 0.34 and 0.35, correct. So, but here if I do the same manual pipetting, I have 0.34, 34 here, 34, and then some are here around 0.32, some of them are 0.35, and then some of them are somewhere here, but the spread is 0.318 or something like that, they are also there. So, if I do 10 determinations, repeat samples of the same analysis, if I do it with automatic machine CARUSEL, I always end up with between 0.34 and 0.35, whereas with this I end up with 0.35 and 0.34. Not only that, but I also get a reading of 0.32, 0.31, 0.33, so many differences. That is with a skilled person. If a person is not skilled, this can even go up to 0.31 to 0.36. In that case, you do not know where is the correct sample delivery, what is the this thing. So, this brings us to the methodology of graphite furnace technique. So, how do we go about doing the chemical analysis using graphite furnace atomic absorption? The electrothermal atomic absorption spectrometry permits the analysis of both liquid and solid samples. Okay. A known volume of the weighed quantity you have to take, the sample is dissolve it in a known volume and then deposit onto the platform or directly onto the tube. Both methods are available in the market. Platform is better, and if you do not have platform, you can deposit on the tube itself, and then it is subjected to a series of stepwise temperature programs. That means heat it to 90 degrees, remove water, heat it to 120 degrees, remove some organic solvents, heat it to 400 or 500 degrees centigrade to remove other organic compounds, and then finally heat it to around 800 to 1000 degrees centigrade to convert all the chlorides and sulfates, etc., to remove them from the sample matrix, and in the finally we make a rapid heating in temperature to 2500 degrees for atomization. So, usually pre-treatment steps are aimed at separating the concomitants or the matrix components as much as possible. So, the inert atmosphere enhances the reducing properties of carbon, leading to better atomization. Okay. So, a majority of the elements of the periodic table may be atomized around 2500 to 3000 degree Kelvin. When you are talking about 2500, 3000 degrees Kelvin or centigrade does not matter, but you can, this is the normal normal practice. Whenever we talk of 2500 or higher range, we talk of Kelvin. So, both pre-treatment and atomization curves may be optimized as a function of the absorbance signal. So, what we have been saying is pre-treatment curve and atomization curve we can optimize to get the maximum signal. Since the atomization emanates from the metal, there is no need to measure the absorbance during pre-treatment. It is important to reduce the sample to metal early in the thermal pre-treatment stage. Before atomization, get it reduced. However, the pre-treatment temperature must follow, it must be below the decomposition temperature of the metal. That means, it should not melt or something like that, which is also the appearance temperature of the metal as evidenced by the absorption signal. So, basically what we are trying to do is we are converting the heating program into two parts. Okay. One is to remove the concomitants, the other is to atomize. So, the appearance temperature of the metal should be optimum. That means, pre-treatment temperature should be very high and appearance temperature should be very low. So, Campbell and Ottaway have postulated a reduction mechanism for many metals in electrothermal atomic absorption. So, what we have is metal, after all the concomitants are removed, metal oxide is there, that will react with the carbon to form the metal and giving you carbon monoxide. So, they calculated for this reaction, they calculated the free energy for the corresponding this reaction and compared the values thermodynamically with the appearance temperatures, and they found good agreement. That means, this reaction is one of the most important reaction in the electrothermal atomization. Okay. So, Sturgeon and Chakravarti again they investigated atomization mechanism, how they get atomized on the basis of thermodynamic as well as kinetic approach, and they proposed 4 mechanisms. What are the mechanisms? I have a metal oxide in the solid form and that reacts with the carbon to give metal, and then the metal is converted into gaseous form, okay, and then it is metal in the gaseous form. So, M can be cobalt, chromium, copper, iron, molybdenum, nickel, and lead, tin and vanadium. Okay. Another mechanism what they said is, suppose I have MOX, that is a variable form of oxide M2O3 or something like that, and then when I heat it, the solid component, it goes to metal and releases oxygen. Here there is no release of oxygen, but it forms carbon monoxide. Here it is releasing the oxygen. So, this kind of mechanism is prevalent for samples containing aluminum, cadmium, zinc and silicon. So, different mechanisms they have studied, and I think it is good for us to know what are the different kinds of ways in which metal is generated inside the graphite tube on the platform or on the graphite tube surface. Okay. So, the third one is metal oxide we have, it forms metal oxide gas straight away, and then that gets reduced to metal and then oxygen is released. This kind of mechanism is prevalent for cadmium, magnesium, manganese and zinc. Okay. Another one is, suppose I take a chloride halogen salt, chloride, bromide, iodide etc., fluorides. What I have is Mx2, that is calcium chloride, magnesium chloride, copper chloride, CuCl2, like that, and then that is remains a solid when I finish and I am finished with the pre-treatment temperature of about 800 degrees, and then that solid will melt forming Mx2 liquid, and then it gets converted to Mx gas, and then later on it will get reduced to metal, and then that is X2. Okay. And then here M could be metal, could be cadmium, iron and zinc. So, mechanisms 1 and 2 here, 1 and 2 are, they require intimate contact with the graphite surface, but here it is only the conversion of solid into gas in third and fourth. So, the decomposition of oxides and halides occur in the vapor stage, it is not in the liquid stage in the these mechanisms 3 and 4. Okay. So, they are these reactions, which one, number 3 and number 4 above, are largely temperature dependent, because vapor has to decompose. It has nothing to do with the carbon contact with the graphite, carbon of the graphite. Okay. So, Fresh and Pearson have also investigated the determination of phosphorus in a graphite furnace. It has been proved that phosphorus oxide, phosphorus dioxide etc., are present around 1800 degree Kelvin. So, that substantial losses must be expected at lower pre-treatment temperatures compared to metals. So, non-coated graphite tubes are sufficiently reactive to reduce the partial pressure. That means, you need not go for pyrolytic carbon atom, pyrolytic carbon platform. You can do it even with ordinary carbon tubes, and that will also reduce the phosphorus losses, because you can work at lower temperature. It has been shown that the from the retained water, methanophosphides gas is formed. To prevent this, what we do is atomization from pyrolytic graphite is preferred and carried out. Okay. So, now these are the discussions about atomic absorption using electrothermal heating. Now, we will discuss a little about spectral interferences in electrothermal atomic absorption. The point is, genuine spectral interferences are as rare in graphite furnace as flame, because it has nothing to do with the sample, right. Electrothermal spectral interference means the resonance line must match. It will match whether whatever is the form of vaporization or atomization you employ, it has nothing to do. If the spectral interferences are there for any element in flame, the same spectral interference you will encounter in the graphite furnace also. Okay. So, but the background attenuation to absorption of the molecular bands like cyanogen, carbon, CO and amino groups. So, those molecular bands are continuous in the flame during measurement, but here in electrothermal atomization we pre-treat them and remove them. So, the spectral interference from the molecular bands corresponding to resonance line are reduced in graphite furnace. I think you should listen to this again and again what I have told you and try to understand what I am meaning to say. So, spectral interferences from the molecular bands are minimum. So, interferences also occur, but by the interaction of the analyte element and condensed vapor phases. Okay. So, molecular absorption by alkali halides and radiation scattering are two important interferences, because the concentration of the concomitants is more than 4 to 5 orders of magnitude than the analyte element in most cases. You ponder over this sentence some more. What we mean to say is the scattering of radiation is more important and the background is higher. So, the background concentration background optical data is 4 to 5 orders of magnitude than the analyte element only in most cases. So, while medium absorption is reproducible, radiation scattering can vary from sample to sample, that is understood, but it follows molecular absorption. This is what I have been trying to tell you throughout this slide presentation. So, this they attributed to molecules migrating to cooler ends. Only when they migrate to cooler ends they do not get removed so easily. Okay. So, molecular spectra may be classified into dissociation continuum and broadband electronic spectra. So, the long wavelength maxima correspond to the dissociation of molecules into neutral atoms, while the short wavelength maxima are attributed to dissociation into the excited atoms. So, the broadband spectra may be due to cyanogen, OH and NH2 bands. The dissociation spectra always exhibits a sharp maxima, as in the case of sulfite ions. If it is sulfite ions, you will see a sharp maxima. Okay. So, these are the problems with sulfite. Sulfite will react with the electromagnetic radiation, whatever is the radiation coming from hollow cathode lamp, and then it reduces to sulfur dioxide and oxygen, and then this can also form sulfur oxides or it can form sulfides, but the lambda max sharp peaks you will get 330, 190, 245 etc. Similarly, nitrogen containing molecular bands NH2 groups exhibit lambda max at 430 and 470 nanometer. They also contribute to the background absorbance. You remember that in all atomic absorption, background absorbance must be subtracted from the sample to get the true analysis. Okay. So, radiation scattering also can arise due to the formation of smoke or soot during thermal pretreatment of the biological and organic samples, or from the sublimed graphite at high temperature. Sometimes graphite also gets sublimed at high temperature. Most of these as well as other molecular bands will not have much impact if the temperature is carefully controlled by the STPF, that is stabilized temperature platform concept, and then it is carefully controlled at the atomization stage itself, then there should not be any problem. But we should be aware of the interferences of this kind. So, by selecting suitable pre-treatment temperature program, numerous matrix components can be effectively reduced or eliminated. Then the analyte element can be analyzed without any interferences. Analyte element can be analyzed without any interference, because we have removed most of the matrix components out of the system by pre-treatment. Okay. Now, this is how the background reduction in platform technique occurs. Look at this. I am trying to determine 40 nanograms of phosphorus. This is the signal peak, 40 this thing. But if I plot the background also, you can see the background is so high, it crosses even 0.3 absorbance, whereas the sample 40 nanograms of phosphorus is less than 0.01 absorbance here. For 0.01 absorbance, background is 0.3. So, 0.3 minus the sample should be 0.3 plus 0.1, 0.31. Out of 0.31 I am subtracting 0.3 background absorbance. So, this occurs due to background and wall atomization. Okay. And if I do STPF, my background is only about 0.25 instead of 0.3, and signal is also for the same 40 is approximately about 0.04 or 0.05, whereas in this case it is just 0.01 or 0.02. So, this is how the platform, stabilized platform concept helps. It removes the background to large extent, as well as 40 nanogram sample is enhanced. So, you can imagine that the background is always higher than the sample signal, but it can be subtracted from the sample plus background. Okay. So, if the analyte element is also volatile, then what happens? A low temperature atomization must be considered, because an element moves out of the system because it is more volatile. So, we should ash it at lower temperature and then allow it to remain in the graphite tube for longer time. So, lower temperature is better, but the matrix components you will not be able to remove because you are atomizing itself at a lower temperature. So, the cadmium, for example, it can be determined in presence of 2% sodium chloride at 750 degree centigrade, whereas sodium chloride does not volatilize. So, if you, these are some of the tricks that we employ depending upon the analysis and the sample matrix. So, when the volatilities of the matrix and analyte are similar, thermal treatment alone cannot guarantee satisfactory separation. This is a very important point. That means, when the sample volatility of the analyte as well as matrix are similar, then you have to do the typical normal background correction. In such cases, what we can do is we can add a little bit of phosphoric acid and nitric acid to the sample, and that helps in ashing the biological and organic samples to remove the volatility of the matrix by forming phosphates and nitrates. They are much more easily removed than the chlorides and sulfates. Okay. So, if there is a problem of equal volatility, consider addition of phosphoric acid and nitric acid to remove the more volatile components than the analyte. Okay. So, ammonium nitrate people have tried routinely to increase the volatility of the matrix and simultaneously reduce the element. So, what is the reaction in such cases? The reaction is sodium chloride will react with ammonium nitrate, simply it will form sodium nitrate, which is easily decomposing at around 400 degrees. It can be sublimed also, it can be decomposed also. Sodium nitrate or both these reactions, both the reaction products are removed at 400 degrees instead of, if you had taken sodium chloride alone, you would have needed 800 degrees. whereas if you just add a little bit of ammonium nitrate, both these products can be removed at 400 degree only. So, these are the typical chemical considerations that are required in atomic absorption measurement of typical elements. This is where the chemistry knowledge comes in useful than the instrument operation. So, at least the background can be considerably reduced, if not totally eliminated, by the use of matrix modification. This is what we call matrix modification, that is, to the sample we are adding a modifier of the matrix. Yes, ammonium nitrate is a matrix modifier, we call it matrix modifier, and we will discuss a little bit more about matrix modifier in our next class.